go ahead and let Brian Britt take it away.
Okay, thank you. All right. Well, good afternoon, everyone. Well, I'd like to start off by sharing a very common scenario experienced by chemistry students all throughout the country and probably almost every day. You have a general chemistry student working their online homework. They recognize the concept being taught. They find the appropriate equation, perform all the algebra and all the arithmetic correctly. They get the correct answer, but then when they put in the answer, it's rejected by the system, and they're told, try again, your answer has the wrong number of significant digits. I think just about anyone who has gone to school has probably had a similar type of experience. So this really is the subject of my dissertation research, significant figures, and more specifically, how they impact the student experience. But what I'd like to do to start off with is talk a little bit about kind of the history. We know that these rules appear in the first chapter of every chemistry textbook, but how did that come to be? Matter of fact, when I was interviewing students for my research, she asked a very valid question. She said, who came up with having any sort of significant figures? And who came up with all the rules as to when you add or when to multiply? And I think it's a very valid question, and I also think that if you asked a pool of chemistry instructors, I'd be surprised if many of them could come up with a good answer to that question. So I wanted to kind of start off that way. Basically, this idea that if you have a result, that its precision ought to be governed by the data you use to calculate it. It's a fairly old concept. You can even find this concept in the writings of Isaac Newton. But kind of the first milestone in the history of significant figures is actually the publication of this book, which is sort of the result of several years of research and teaching by Dr. Silas Holman all the way back in 1892. And so he published this work, and in it we'll find a lot of, it was sort of considered by many to be the first attempt to try to come up with a systemic way for handling precision. And so if you look at the pages of the book, you'll find some interesting things. You'll find, for example, the addition and subtraction rule that we're all familiar with. There it is, right there in the book. It also mentions operations like logarithms. It mentions multiplication and division, although I did think it was kind of interesting when it talks about multiplication and division, the rule that he has is something completely different from what we have nowadays. And so this was sort of a first attempt to provide some sort of a system for it. There was by no means any standardization as the years went on, until finally in 1993, there's this standards organization called ASTM. That's the American Society for Testing and Materials. And they finally decided to standardize these rules into what they call standard E29. And that is where those rules are held today. So if you wanted to know, like, where do these rules come from, it's not the chemistry textbook, it's ASTM, standard E29. You can find those there. But what I thought was kind of the most important thing the most interesting thing that I learned as I was kind of digging into the history came from this article right here. I highly recommend this article for anyone that's interested in this. So Dr. Ashley Carter published this article called Evolution of the Significant Figure Rules, which deals with a lot of the history. And she made a really interesting point in this article that in the field of the physical sciences, the education, we didn't really see these rules for a rather long time. It wasn't until about 1980 or so. And so she kind of describes it this way. She says, the apparent lack of significant figure rules in physics in the first half of the 20th century is most likely due to the popularity of the slide rule, which we have pictured there. The number of significant figures in the computed answer is limited by the precision of the ruler, typically to 3 digits. This eliminates the need for significant figure rules in solving textbook problems. So she continues, the explosion of significant figure rules in physics textbooks in the 1980s is almost certainly due to the widespread use of the pocket calculator. Texts that mention the slide rule do not have a section devoted to significant figures, while texts that mention the calculator do have a significant figure section. And she concludes, the introduction of significant figure rules into physics is most likely a response to careless students writing down the 10 digits shown in their calculator. Now, it has to be noted that Dr. Carter works in the field of physics education. What about chemistry education? Well, if you search through the chemistry education literature, you find a lot of these same types of discussions were going on in like the late 70s and the early 80s. Just to kind of give you a couple of examples, here's an op-ed piece in Journal of Chemical Education back in 1979 from Thomas McCullough. I include this quote because it just makes me laugh. He was not a fan of the pocket calculator, and he had this to say. He said, in the field of science, a corrupting power is the pocket calculator. which easily, quickly, and accurately performs all manner of mathematical operations at the push of a button or two. Unfortunately, the calculator does not know how to manipulate significant figures properly and imparts this ignorance to the unwary student who dutifully and naively records all the pretty luminous numbers as they appear in the readouts. Definitely no fan of that, so we can see the problem articulated in the field of chemistry. I wanted to share another quote from that time period by Dr. George Wieger that shares a bit of a different perspective, and it aligns really nicely with what Dr. Carter was saying. He says, "What about significant figures? Clearly a calculator-related problem. I'd like to suggest that it's not necessarily true that students 10 years ago, by not violating significant figure rules, demonstrated an understanding of the restrictions. Given the tools available, that is to say the slide rule, you could not produce answers with excess significant figures." And also, I had the fortune of talking with our own Dr. Pringle the other day, and I asked him about his experience taking chemistry in college in, I think, 1969 it was. And he, what's that?
59.
1959, okay, even earlier than that. And he corroborated a lot of the things suggested by Dr. Carter. He mentioned how back then he would do calculations using the slide rule, and the slide rule typically gave answers to 3 significant figures, and there just was little to no emphasis on the significant figure rules. And he gave me this college chemistry textbook from 1951, and it's true, if you page through this whole thing, it doesn't mention the significant figure rules once, ever. And so it does. Oh, and also he mentioned that when he started teaching here at UNC, again, there wasn't much emphasis on the significant figure rules. So it was interesting to see someone who lived through that time period kind of corroborate some of the things mentioned in the literature. Okay, so that's kind of a brief history of how these rules came to be and how they came to form part of the first chapter of almost every general chemistry textbook. So kind of getting to my study, I was interested in 2 things mainly, is sort of the mental workload associated with significant figures, and also student experiences and what their opinion of the significant figures rules and to what extent they found value and meaning in them. So to help me with this, I have essentially 2 theoretical frameworks that I'm using. The first is cognitive load theory, which essentially says that human working memory is limited. And so if we want our instruction to be effective, we need to take these natural human limitations into account and avoid giving people too much to think about at one time. And if you don't, the result could be cognitive overload. And if a student is cognitively overloaded, there is not effective, meaningful learning taking place. Just wanted to share a couple useful definitions. There's this idea of intrinsic cognitive load, which is sort of the inherent mental workload of any given task. And then there's this idea of element interactivity, which is one of the major factors that determines what the intrinsic cognitive load is. And what element interactivity is it's essentially the degree to which the various facets of a problem are interconnected and require thinking about simultaneously. So just to kind of give you a chemistry explanation of this, here's an example of a chemistry question with low element interactivity. Write the atomic symbol for sodium, lead, and gold. You don't need to think about multiple things at the same time in order to answer a question. It's just a mere matter of retrieving something from your memory. But here, by contrast, is something that's very high in element interactivity. Balance the following equation. So we know from our experience balancing equations, you can't just think about one coefficient in isolation. You have to think about all 4 at the same time, because making a change to one coefficient will propagate through the equation and create changes in other parts of the equation. So this is an example of high element interactivity. And with this idea of element interactivity in mind, I want to kind of go over what a standard problem looks like when you are applying significant figure rules. So anyone who's taken first semester general chemistry will recognize this heat transfer problem. We use that old equation Q equals mc delta T to figure it out. So here we're given a mass of water, we're given a specific heat of water, and we're given a starting and a final temperature, and we're asked, how much heat is required to make that temperature change. So we set up the problem just like this, but if we're asked to apply significant figure rules while we are solving this math, it's not a matter of just punching these numbers into the calculator and getting an answer. What you need to do is take all of the steps in the procedure one by one. So if we're applying the mathematical order of operations, we need to look at the subtraction first, and we have to say, okay, I need to apply the addition-subtraction rule. I see this has 1 decimal place. I see this has 1 decimal place. So when I subtract that, my intermediate answer needs to be 5.0. It can't be 5 like the calculator would tell you, otherwise we're not going to have the right number of significant digits. So as you have thought about that first rule, done your subtraction, you then get this intermediate expression here. Now we have 3 terms that we're multiplying together, and now we have to think about a different significant figure rule. We have to think about the multiplication rule, which tells us that we need to round our answer so that it has the same number of significant digits as the factor that has the fewest. So we go, okay, well, it looks like we have 3 here. Oh, that's also 3. I made a mistake there. 3 here, and then 2 there. Okay, so then I need to round my answer to 2 significant figures. So we'd initially get 47.025 on the calculator, and then we would round that to 47 joules. I think it's worth pointing out that even though we were given data here, or we were given numbers to 3 significant figures for every single one, the final answer only has 2 significant figures. So this is not something that you can do after the fact, after you have done all the math. We need to think about these rules as we do each mathematical step. And so from a cognitive load perspective, thinking about this idea of element interactivity and how many things do we need to handle simultaneously, one could hypothesize that applying these rules to math would result in some increase in the intrinsic mental workload of these problems. So that was the first theoretical framework that I was going by when I was doing my research. The second is something called expectancy value theory, and this was the framework that I was using to kind of help interpret the results of the qualitative interviews. As you can see, expectancy value theory has this very complicated flowchart. It has many elements that sort of interact and affect one another. Just to create a simpler visual, I was mostly interested in these parts that I've kind of highlighted in red. And so I want to present this. It's still the same information, just in a little bit of a cleaner format. The basic idea behind expectancy value theory is to determine what sort of factors affect a person's motivation and affect a person's willingness to engage in a particular task. So just to kind of go through these, one of the main ones here, and the main ones are kind of these 3 things that I've highlighted here. One is expectation for success. If someone is considering doing a particular task, engaging in a particular activity, one of the basic questions they ask themselves is, can I do this task? And if they believe they can succeed, they're more likely to do it. If they believe they're going to fail, they're less likely to do it. The other thing is subjective task value. So earlier we asked, can I do this task? Now we're asking, do I want to do this task? Is there any value in this? Is there any profit in this thing that I'm going to do? And that can come from a few different sources. One of them might be interest enjoyment. So for example, if you solve crossword puzzles, you probably do it because you find it interesting. That would be one. And so that particular task would have value in our eyes. Another could be utility value. So for example, if you were going to visit a foreign country, you decide, you know what, I might want to learn a bit of the local language so that I can communicate with the people there. That would be an example of utility value. And then finally, we have cost. What is it going to cost me to do this task? Is it going to cost me money? Is it going to cost me time? Is it going to cost me mental effort? There's other types of cost as well. Affective memories. If you have kind of a negative association with this task, maybe a little bit of trauma, that kind of emotional response will make you less likely to want to engage in that task. Or is there a high cognitive cost? Is it going to make you have to work very hard mentally to achieve this? So these would be the various different things. There are a few other things in the thing. For example, socializers' beliefs and behaviors. Socializers are the people that have the most social influence on you, and depending on their attitudes, their beliefs, their perspectives, those might influence you to maybe believe that you could be successful or not believe you could be successful, and they might determine the extent to which you find value in a particular thing. And so this was the basic theoretical framework that we used when helping interpret the results of the interviews that we conducted. Okay, so research questions here. The main ones were 1, how do the significant figure rule constraints affect the mental workload of chemistry problems? 2, to what extent does the increase in mental workload due to significant figures, if there is any, to what extent is it correlated with student math anxiety? The hypothesis was that if there is added mental effort with significant figure rules, maybe it's not the same all across the board for all students. Perhaps the degree to which someone feels comfortable with math might be an influencing factor there. And then finally, how do students describe their experiences with significant figure rules? And this was basically the question for the qualitative interviews. So what we did is we took a total of 40 participants from 2 second semester general chemistry courses, They took a significant figure assessment that featured 3 questions. There was a stoichiometry question, a heat transfer question, and then a temperature conversion question. It was a counterbalance designed with 2 conditions with and without significant figures. What that means is that half of the students saw those 3 questions with the significant figure rules, then they did them again without significant figure rules, and then for the other half, the conditions were reversed. Half of them saw them without, and then they saw them with significant figure rules there. And then after each question, they rated the mental workload of the questions using something called the NASA Task Load Index. And so let me just give you a few visuals. So this is an example of the stoichiometry question that they saw. Now you'll notice this has been greatly simplified, and it's been simplified in 2 ways. One, we have actually provided any relevant equations and also substituted the relevant numbers into those equations. So in the case when the student didn't have to do significant figure rules, they just had to punch these numbers into a calculator and get an answer. And then in the condition with significant figures, same thing, they had to punch the numbers into the calculator, but they had to think about significant figure rules while they did this. And the reason it was structured this way is if there was any reported difference in mental workload, I really wanted it to be due just to significant figure considerations and not due to variations in, say, chemistry content knowledge or variations in a person's math ability. I really wanted SigFix to be the only factor at work here. So that's why we provided this simplified problem set. And so in one half it said round your answer to the appropriate significant figures, and then in the other second half of the assignment it didn't have that instruction. It said basically report these answers however you wish. And then like I said, after each question, they used this NASA Task Load Index. It has 5 scales here. So they, from a scale of 0 to 100, the students would rate, how mentally demanding did you find the problem? Temporal demand, how long do you feel it took you to do this problem? Performance from 0 to 100. The left side means I didn't have any problems with this, I did it absolutely perfectly. And then the opposite end of the scale, I completely failed to do what I was asked. And then lastly, we have effort and then frustration. How insecure, discouraged, irritated, stressed, and annoyed did you feel while you were doing this problem? Okay. And then the last thing students saw is they answered this very simple question on a scale of 1 to 10, how math anxious are you? For the qualitative portion of these, the interviews typically lasted about 10 to 15 minutes. They were transcribed, they were coded in vivo. They were analyzed using both inductive coding and deductive coding, and like I mentioned earlier, we used the expectancy value framework to kind of analyze these things. And we had an intercoder agreement of 88% for those interviews. Here are some of the questions. The interviews were semi-structured, but generally all students were asked these questions. For each question, explain how you arrived at your answer and how you decided to round it. So I gave the student their assessment and said, walk me through question 1, what went through your mind, how did you determine how to do things? 2, a very open-ended question, describe your experiences with significant figures. 3, because we were interested in expectancy for success, we asked, if you see a problem requires you to round answers using significant figure rules, how does this affect your expectation that you'll be successful? And then 4, in your personal opinion, because we were also interested in value, in your personal opinion, what is the value of including significant figure rules in general chemistry problems? So these were sort of the basic questions that were asked of everyone, and then obviously conversation sort of flowed from there. Okay, so I'm going to present the results of the qualitative study first. Just to kick it off with I like to put some interesting quotes from students I heard. I've never been told the significance of significant figures, which I thought was a pretty succinct, snappy way of putting it. Just to kind of remind you what the expectancy value framework is, when we're analyzing the interviews, we're looking for things that would fall under the category of cost. Is this person describing any sort of cost? Is this person describing anything about their expectation for success? Are they mentioning something about how their socializers in their life have affected their perception of significant figures? And finally, are they making any statements that could be classified as value statements about significant figures? So we're going to kind of go through these different parts one by one. So first, under socializer influence. Some students mentioned teachers, and when they did mention teachers, one of the more common themes was they felt their teacher hadn't provided sufficient justification for the significant figure rules. So Mariana said, I think they're silly. When it was explained to us why we needed them, it didn't feel like enough of a reason. I remember my professor showed us a ruler, and I don't even remember why we need them. But I remember sitting in that lecture and going, but why? Like, for real, why? because they don't feel necessary. So there were a number of students that had similar expressions to that. Some students felt that their teachers actually didn't emphasize them very much by the nature of the structure of the course. So in the case of like multiple choice assignments. So Kylie said, on the exams, there's very few cases where we have to round. It's multiple choice, so you pretty much know if your answer is right or not. You don't have to think about your rounding rules for significant figures because you can see your answer out of the multiple choice. In contrast to this, there were a few students also that talked about the opposite thing, how their teacher emphasized them to a very large degree to the point that it was just punishing. So Charlotte, for example, said, my chemistry teacher was under the impression that we all just knew what sig figs were. So it wasn't till about 4 weeks in that I actually realized what sig figs were, because I failed my first test. And she's like, you only failed because all your sig figs were wrong, but everything else was right. So after that, I just dreaded significant figures. So here we have a teacher emphasizing things to a pretty high degree. So that was teachers. Some students also mentioned peers. And when we think about peers can kind of be beneficial in the sense that if we witness a peer doing something and succeeding at a task, that can kind of help increase our own self-efficacy. But conversely, if we see a peer not succeeding at a task, that can also negatively impact our expectation for success. So when students did mention their peers in connection with sig figs, it was pretty much always in the context of some degree of struggle or difficulty. So we have James saying, I and every other student I've talked to who has taken general chemistry has struggled with it. And I consider myself to be someone who's good at math and good at general chemistry. I've succeeded in both courses. I've thought about tutoring in the future, and this has been the one thing in my journey of chemistry that's been at least a little bit like a roadblock. So we had expressions like that as well. So kind of in summary, this little piece of the puzzle we're creating, when students talked about socializers, it was typically about peers and teachers. And when they talked about peers, it was difficulty in connection with significant figures. And with instructors, the main themes were kind of instruction that just didn't seem to be enough to justify it, or maybe lack of emphasis there. So speaking about the kind of the second thing, cost, we identified emotional cost when people would talk about kind of negative feelings in connection with significant figure rules. Expressions of frustration and annoyance were very, very common. So Harper, for example, said, looking back at exams, you're like, oh, I missed that half a point because I didn't round to the right significant figures. The answer was right, but I didn't have the correct significant figure. So it's just frustrating in your head to be like, I should have missed that half a point. So we have frustration or annoyance. Another common expression, confusion and uncertainty, just not really knowing what to do. So Lucas simply, I second guessed myself, and I wasn't sure sometimes which one to use, like which rule. Another thing is participants very common spoke of stress and anxiety. So Alina, for example, mentioned when she's trying to calculate sig fig rules on like an exam, I kind of have a little panic moment. Similarly, Audrey, it was very anxiety-inducing. So these would be examples of sort of emotional costs or negative associations with significant figures. So that would fit in right there. We can also think about costs in the terms of cognitive costs. So we were looking for times when students would describe sort of an extra mental workload associated with these rules. So some spoke of how sig fig rules made the problems more difficult. So it's very hard to finally understand, especially long equations would have all these decimal places, all these rules, and addition and multiplication combined, and all of that made it a lot harder, for sure. So this was another really common expression that we heard from students. About half the participants mentioned how it also increased the time that was required to solve problems. So Samantha said, there's a lot more going back and triple checking, that she was talking about exams here, going back and triple checking to make sure I'm following those rules. It definitely takes longer. And then, even if I put an answer down for a problem, once I go on to others later in the exam, I'll come back and I'll re-put it in just to make sure. So we have this talking about general mental difficulty and also talking about sort of an increased time to solve problems with these. So these two things we would consider sort of an increase in mental workload as being sort of a different form of cost going into this. Looking at this next part of our theoretical framework, value, and remember we're looking for kind of, does anyone talk about anything concerning interest or enjoyment of this particular thing? And what are people saying about their perception of value of significant figure rules? So here are actually, I'm going to talk about a factor that includes, before we get there, going to talk about something that impacts both cost and expectation for success. And I'd say this was the single most common expression across all interviews was difficulty with ALEKS. So participants use ALEKS for their homework. It uses this mastery system whereby you need to get a certain number correct in a row in order to pass one topic and move on to the next. If you don't, then it resets your progress. So over 75% of the participants reported some degree of frustration with the ALEKS homework because of SIGFIG requirements. So Liam said, I'm dreading getting to the end of the question because I don't want to go through the entire process of plugging in all these numbers, like in a stoichiometry equation, find all these molar masses just to get the wrong number of significant figures and ultimately miss out on the question. And then if you miss one, you lose all that streak you built up and you got to start back from 1 out of 5. So it's just like a roadblock. Some students were even more forceful with this. We have one module on our ALEKS that each time we try to do it, it has something completely different to say. So it's hard to anticipate what it's trying to say to us versus what we're finding online or being able to know and do. So this person had the impression that ALEKS was changing up the rules every time that they did it. It's completely changing. It's like we can't just gauge it based upon the answers because how we're rounding and how it's rounding is completely different. So it can be hair-ripping. I've cried. Actually, I had 2 students mention crying in connection with their ALEKS. I have someone saying, yes, okay, I have a couple in the audience saying the same thing, crying out of frustration. So, yeah, it's definitely something to keep in mind. So this would be an example of something that would affect both cost because you have negative memories associated with ALEKS assignments. And if you have these experiences of failing to get sig figs right because of your ALEKS homework, it's definitely going to decrease your expectation for success when you're asked to do this. Okay, and then finally getting to this portion, the subjective task value. Remember that first thing I mentioned was interest and enjoyment. There wasn't much interest or enjoyment among students with regards to significant figures. I didn't put it on here, but I did have one person out of 40 say that she liked significant figures. She basically said that because she has a tendency to rush and go fast, then she kind of liked the opportunity to kind of slow things down a bit. But she was the only one that said anything positive about significant figures. So here's this person was pretty blunt. I said, tell me about your experience. All I said was, tell me about the experiences you've had with significant figures. And she said, yeah, I hate significant figures. I think everyone feels the same way about significant figures. We all hate it with a passion. This was obviously the most forceful expression, but it was also very common. A lot of people express things in a little bit softer terms like annoying or frustrating, but there was not much interest or enjoyment when it came to the significant figure rules. So that interest or enjoyment would kind of slot in here. If you don't find something particularly interesting or enjoyable, you will not value it. And then the last thing is utility perception. So a question I'll get to in a second, but over half the participants said they couldn't see the purpose in the significant figure rules. They didn't know why they were learning them. So here I asked the person, in your personal opinion, what is the value of having significant figures in chemistry? I don't think there is value. I think if you're off by one significant figure, it's not going to matter in the scope of the class. I feel like as long as you know what the concepts are and you can apply yourself to those concepts, you're going to be fine. So that was one perception here. I think this person was particularly interesting, Alessandra, because she mentioned she had a number of learning disabilities. She had anxiety, and she mentioned something called dyscalculia, which is like dyslexia, but it's for numbers, so it's mixing up numbers. So I asked, she said, I don't really think about significant figures, to be honest, like unless I absolutely have to, and says, unless it says in the question, I don't really think about it that much. And I said, okay, well, what's the reason that you don't? And she says, it gets so much more complicated than what I already have going on. And I just don't understand like why they need them. It's like, why does it matter how much we shorten them or not shorten them? And yeah, I've never liked sig figs. I have real animosity. That's I don't know I've ever heard a student describe any chemical topic as having real animosity. So she was pretty passionate there. So of the 40 students, I think it was about 9 or 10 or so, that the ones that did suggest there was value in significant figures, they were almost always talking about a sort of real world lab type context. So for one person said, I think maybe if you're a chemistry major, if you're doing lab and titration specifically, it seems very important because you're talking about chemical equations that, you know, decimal points do matter. But I think for an environmental science major, it doesn't really matter to us. in a lab, here's another person that said, I know when you get down to some really important, like you're mixing two very small amounts of substance or something like that, maybe having correct significant figures could be really important. I don't know entirely how that works in a lab setting or like an actual chemistry setting, but I can see that there could be some importance. I think it's important to point out, like, ideally, what an instructor would want to hear from a student is something like, well, experimental measurements, their precision is limited by the precision of the data we collected, and so we should be responsible in how we report our answers. But not a single student out of 40 said anything resembling that. When they did suggest there was value, it was kind of these sort of vague statements with appeals to like, oh, you need to be accurate or you need to be precise. But we didn't really hear kind of more specific expressions on that. So that would be the last portion of our theoretical framework. And so, again, what is all this building to? Well, these are the various factors that impact this center circle here, achievement-related choices and performance. What does a person choose to do, and how well do they perform on their task? So what were these students' achievement-related choices? Well, the big choice that we saw while they were doing the assessment is abandoning significant figure rules, just not doing them. Even though we specifically asked them to do them and to apply the rules, very often that didn't happen. So very few participants persisted in applying significant figure rules throughout all three questions. Again, remember I asked them, explain to me what you did here. And it became rather obvious fairly quickly that they weren't applying the rules in the way that they were supposed to. So students tended to abandon the significant figure rules when the problems featured sort of mixed mathematical operations. So if it was just one thing, it was okay. But as soon as we start combining them and you have to think about the rules multiple times and different rules each time, that's when it really got hard for people. So Jacob, for example, said, it's confusing. I feel like unless it's straightforward, where it's just multiplication or just addition, it's manageable. But then, once you start combining the two in different ways, that's where I completely lose it. I'm like, well, I'm just going to guess at this point. So we see this idea of abandoning this. I see some nods coming from the students as well. So, for example, Kylie, when I was asking about how she did sig figs on what problem, she said simply, I didn't do any significant figures. I only waited until the last number I got. And this was the other really, really big thing that came out of the qualitative interviews. About 50% of students reported doing something kind of like this. It happened so often that I decided it needed a name. So I called it the post hoc approach. Post hoc in Latin means after the fact. So the way the post hoc approach is students just do all the arithmetic without thinking about sig fig rules at all. They get an answer, and then to decide how to round that answer, they look back at the things that they were given and they try to match it to some number that they saw in the problem. This was very, very common. So here's a visual of what that looks like. This is a temperature conversion from Kelvin to Fahrenheit. We can see that here the student is doing all the math completely properly. They get the right answer. But while they were doing this, they were not thinking about sig fig rules at all. So first they get a mathematical answer, and then to decide how to round the answer, she looks up and goes, 9 is one significant figure, so let's just use that. And that is how 161.33 becomes 100. So that is an example of sort of the post hoc approach in action there. One thing that wasn't super clear from my interviews, because I didn't really follow up on this, is were they doing it this way because that's the way they really thought they were supposed to do it? Or were they doing this just like intentionally as like a sort of a labor-saving method? And I can tell you at least a few people were very honest. So Lucas was one of them. He said, so at first, talking about his homework, I was really trying to get the correct sig figs, but it would take me a while trying to get it, and I'd get it right like half the time. And after that, I figured, well, it's going to take me way longer to try to do it. If I just do it without using the correct sig figs, I have a 50-50 shot of getting it right anyway. So I just kind of do that, and it takes less time, if that makes sense. So here we have a very conscious decision to just ignore all the rules, decide how to round it based on here, and maybe half the time it works out. And so this is a strategy adopted by a lot of students here. So these were kind of the major themes that we found in the qualitative portion of the interviews. So as for the quantitative study, again, I like to introduce it with a student quote. I have to focus on the significant figures, otherwise it's not going to be right. It scares my brain. So I was interested in the quantitative study to try and quantify how fearful brains were while they were doing this. So just to kind of give you a quick review, we had 3 questions. There was a stoichiometry, a heat transfer, and also a temperature conversion. They did all three of these, two versions with sig figs and without sig figs. And then we quantified it using the NASA task load index here. So just kind of show you an overview of the results. Here we have for each question 1, 2, and 3. These are box plots. The teal represents the range of scores. Remember, these go from 0 to 100. The range of scores on the non-significant figure portion for each 5 of these. And then the ones in salmon are the box plots for the ratings for the significant figure portion. So just at a glance, we can see some pretty noticeable differences in all of these. And then this is a slide not necessarily to look at, but these are the sort of the average for the non-sig fig, for the sig fig, the difference. And then we conducted a paired t-test to see if these differences were statistically significant. And for each combination of question and scale, for all 15 of them, they were all quite significant. And I think it's worth pointing out that the differences that tended to be the highest were the ones on question 3, which was the temperature conversion. And that kind of made sense. The hypothesis was that because the temperature conversion question requires the highest degree of mixed operations, that would be the most difficult one when we introduce sig figs into the mix. Okay. In addition, we measured the students' times. Now, times tend to not be normally distributed, so we use the medians. We can see kind of the median time of the non-sig fig problems here, and then the differences here. So we went from a median time of about a minute on the non-sig fig problem here to almost 2 minutes, so an increase of almost double. We went from 0.87 to 1.3 here, so an increase of about half a minute. And then on the third one, which again students reported the most difficulty with, because it had the greatest number of operations, we went from about 0.66 minutes to almost tripling it to about 1.8 minutes. And so this was the largest time difference. And then we conducted a Wilcoxon sign rank test, and all of these differences were statistically significant. And then lastly, on the we wanted to see, does this increase in cognitive load correlate with math anxiety? Here what we did is we took the average score for each 5 of the NASA task load index items and averaged them into a single score, the differences between the two. And that was sort of like an estimate of the overall difficulty that a student had with significant figures. And then we plotted that difference here against the reported level of math anxiety. And we can see upward trends in each one of these. And surprisingly, the magnitude of the Pearson's R correlation coefficient was about the same in all 3 cases, just a little bit under 0.4, 0.38, 0.39. So we did see, and so these were all statistically significant. And then lastly, just for time purposes, I'd love to go into more detail about this, but I'm going to have to skip over it, I think. Oh, wait, no, actually. No, I think I have enough time. Okay. I was interested in, what would be the success rate? What percentage of students were able to successfully use these rules and get a quote-unquote textbook correctly rounded answer to each one of these? So for question 1, stoichiometry, it was 37%. For the second question, the heat transfer one, it was 90%. And for the last question, it was only 15%. I do have to say a few things about these numbers because they look a little bit strange. You might wonder, why did only 37% of students, why were only 37% able to get a correct answer on the stoichiometry? Well, this was kind of a review of what the question was. Because this was 3 significant digits, the answer should have been rounded to 3 significant digits. But what we saw a lot of students doing, basically about 63-ish%, is they did their math first, and then to decide how to go back and round it, they said, oh, this is 1 significant digit right here, this stoichiometric coefficient. So I need to round it to just 1. And so that was the main reason why most people did not come up with a correctly rounded answer for question 1. Question 2 or 3 is rather interesting to talk about. Remember how I talked about the post hoc approach where you just do all the math, ignoring sig fig rules, and then to decide how to round your answer, you just go and look for the thing with the smallest number of significant digits? Well, it turns out in question 2, if you apply that approach, you get the right answer. But if you apply that same approach to question 3, the temperature conversion, you do not get the right answer. So that's why question 2 has a success rate of 90%, whereas the second question, or the third, only has a success rate of 15%. And I just want to call to mind something I mentioned earlier, this perception, because this student was not the only one that talked about this perception that Alex was not consistent in changing the rules all the time. This now starts to make a little bit more sense, because if this is the approach that students are using, you're gonna get lucky a fair amount of the time. And so it might succeed on one question, but on the very next question it will fail. And so it's understandable that the students can say, hey, what's going on? Like, why are you being inconsistent about this? So this is probably the reason for that Alex perception. Okay, so just to kind of sum up the quantitative findings, the significant figure rules we found represent a statistically significant increase in cognitive load. And this increase in cognitive load does appear to correlate with the student's reported level of math anxiety, meaning students that enter general chemistry already kind of predisposed to have a difficult time because of their math ability might struggle even more with significant figures compared to their peers who feel more confident in their math abilities. And then we also found that there was a statistically significant increase in task completion time. Okay, so those are the results of the two studies there. What is the implication of these results for teaching then? So again, I always like to introduce this with a quote. I feel like this concept should be more for upper level classes. Gen Chem 1 is very introductory and it's just overwhelming when it's thrown at you. So the first thing I would say as far as implications for teaching go, we would just kind of suggest that professors should bear in mind that these rules do add extra cognitive load, extra mental workload to the problem-solving process. So if you ask a student to complete some multi-step problem while also using significant figure rules, just know that it's not a trivial task. And so we would kind of urge instructors to be reflective and kind of ask themselves, to what degree do I want to emphasize these rules in my course? Is there enough pedagogical benefit to justify the added workload if we are having students use these significant figure rules? I think this question becomes especially important during like exam situations. So if you have a student in this sort of high pressure situation, time constrained situation, they only have about 50 minutes to complete an exam that might be a substantial portion of their grade. We could perhaps ask the question, how much time do we want students spending deciding how to round their answer? Should it be 1 decimal place or 2 decimal places? Maybe that might not be the optimal time to be assessing students on these types of things. And kind of on that note, we can ask, maybe it might be a good idea to maybe go back to how the way things used to be. So we talked about how in general chemistry, it used to be that as a general rule, you just told students to round everything to 3 significant figures. And maybe for an introductory level, a freshman level general chemistry course whose population is largely non-chemistry majors, maybe that might be sufficient. And maybe for the chemistry majors, perhaps they can kind of get finer points of error propagation when they go on to analytical chemistry. So that would be the first thing to think about. So be aware and reflect on the cognitive load increase associated with significant figures. The second one, again, this is one of the major points, that significant figure rules under some circumstances may cause a lot of trouble with online homework systems. So that was really the #1 source of frustration with that. So maybe instructors, again, even if you don't necessarily emphasize these rules very much in your course, perhaps you could ask, is the online homework system I'm using, is that aligned with my goals? Or is it putting undue pressure on my students? So maybe make sure that the your choice of online homework system is reflecting that. I wanted to include this quote from the paper I mentioned earlier from Dr. Carter. She made the following observation. The significant figure rules were not intended as a deterrent for 10-digit calculations, but as a means of quickly determining error propagation in the laboratory. They were originally designed as an aid to help students avoid laborious calculations, not as a way to add extra burden to the students. So these reasons lead me to conclude that the use of significant figure rules in homework problems may be ill-advised. So that would be kind of the second main point. And then for the third point, again, I think if we want students to appreciate these concepts of precision and significant figures, the single biggest obstacle to that is the perception of a lot of students' part that these rules are meaningless. They don't really know why they're being taught. And I think that really has to do with sort of the standard approach that is taken in lecture. So again, sort of the textbook approach goes something like this. An instructor will stand up here and tell students all measurements carry uncertainty, and therefore all results that we calculate from those measurements also carry uncertainty. And that makes perfect sense, and all the students will agree to that in the abstract. But then what often happens in chemistry courses is they go, okay, now here is a list of significant figure rules, memorize these rules, also memorize this list of exceptions and caveats, and then internalize and apply these to every calculation that you do. This might not be the most effective approach to things, and in fact, when I was going through the literature, I found something saying basically that same thing. So this paper from 1995, they say many teachers and textbooks take a rule-based algorithmic approach to this topic. And as a result, students sometimes develop a poor first impression of chemistry from this boring rote memorization lesson. And I would add to that, chemistry lecture might not be, a lecture hall might not be the most appropriate place to discuss these concepts. Because again, if these rules were originally intended for measurements in lab, well, in a lecture hall, we don't take measurements. We don't make computations with measurements. The numbers that we work with are fictitious. They come from a textbook, they come from an online homework system, they come from the professor's imagination. So in that context, one could ask whether it makes contextual sense to even speak of precision when we have students calculating fictional results from fictional data. To kind of contrast this, lab really is the ideal place to talk about these concepts, because in the lab, in contrast to lecture, in lecture, precision is a bit of an abstract concept, but in lab, where students actually take measurements and actually calculate real results from these measurements, it's not an abstract concept anymore. The instructor can help the student to see firsthand in a very concrete way how their measurements are subject to error and how this error propagates when you do calculations to lead to the error on the final answer. And also I would say that because students are taking these measurements themselves, they generally have more of a sense of ownership over their data and more of a sense of ownership of getting a good result. And so I really think these points can be made in a much more clear way, a much more meaningful way in lab. Okay, so I think that's about all I have from you. I want to thank first and foremost my advisor, Dr. Weinrich, for all of her help over the years. Tim Jones, who's been a great friend over the years. In addition to all the grad students who have created this very lovely atmosphere in the grad office, I appreciate you all. My committee, my parents for their support, and also my grandmother. And here are some references, and that's all I have for you.